Okay, this is the extra credit opportunity for test version C. Please make sure that you're writing your answers neatly and in a nice orderly manner so we can grade them and give you the full credits points that you deserve. So here we go. The land of Nod is populated by all sorts of interesting creatures. Among them is the goblin. In order to attract mates, goblins slobber sometimes as much as a gallon a day. The trait is embedded in the genetic makeup of the goblin, and the gene is carried by both male and female goblins. 95% of the little goblins carry the slobbering gene. The little goblin's biological mother carries the slobbering gene. If not, excuse me, 95% of the little goblins carry the slobbering gene if the little goblin's biological mother carries the slobbering gene. In addition, it is known that 85% of adult female goblins carry the slobbering gene in the land of Nod. In the land of Nod, the genetic trait of slobbering randomly appears in 25% of little goblins, in which the female parent does not carry the slobbering gene. Well, that's great. I have a whole bunch of nonsense to try to make order of to solve the problem. And that, to me, is confusing. Whenever I have a confusing problem, I think table. And then I happen to check, and I happen to have three numbers. And that three numbers isn't a guarantee of a table, but it's a pretty good indication that this might be something that I should consider. So if I'm going to make a table, I need to identify the variable or the number associated with one, or I need to be able to assign something about these numbers. So let's see what we can figure out. So the trait is embedded in the 95% of the little goblins carry the slobbering gene if this is a condition. As soon as this is a conditional, that makes that two variables, all right, because it's conditioned. The little goblin carries it if the mother does, so it's conditioned on whether or not, so it's conditional, two variables. In addition, it is known that 85% of adult females carry the slobbering gene in the land of Nod. That seems to be only on one variable. Just females, 85% of the females carry the slobbering gene. There's no if or et cetera, indicating this is a special group or part of a group. So 85% of female goblins carry the gene. This looks like single variable. Then we go over here. In the land of Nod, the genetic trait of slobbering randomly appears in 25% of little goblins, in which the female does not carry the slobbering gene. So 25% of little goblins carry, in which it appears in 25% of little goblins from the group of female parents that do not carry the slobbering gene. So this is conditioned on what the female parents are doing. So consequently, this is on two variables. So the one that looks like a single variable is 85%. So let's start with the table and see if we can't start to organize some of this information out. Once again, not 100% guarantee, but it's a pretty good likelihood that if we have a lot of information, we should be using a table to help organize it. And three numbers usually indicates that the problem is a table problem. So here we go. Always make my window. Hope I made it big enough, 1.0. It's the one number I always know. All right, so 85% of female goblins carry the slobbering gene. So this is going to be 0.85. 1 minus that is 0.15. So I can write a 0.85 here and a 0.85 here, 0.15 here, and 0.15 there. All right, so what is this? Oh, these are females carrying the gene, females with the gene. This one is females no slobbering gene, and so I'm just called FNG, females no gene. All right, so now what do we have? 95% of the little goblins carry the gene if the mother carries the gene. So little goblin gene, little goblin no gene. And I know you can abbreviate it maybe even shorter. But little goblins carrying the gene and females carrying the gene happens to be at 0.95. Well, because this is 0.95, this makes this 0.05. So let's multiply this out. 0.85 times 0.95 is 0.8075. So the probability that a randomly selected goblin that both of them, the little goblin and the mom carries it, is 0.8075. All right, and then 0.85 times 0.05 tells me that we have a 0.0425. And I should check myself. This plus this should equal that. And if it does, we probably are doing things right. Not 100%, but that's probably a good indication. All right, we already have the 85%. So in the land of Nod, the genetic trait of slobbering randomly appears in 25% of little goblins. So little goblins have the gene, in which the female does not. So female not, this is 0.25. Female not, little goblin carrying it. The complement of that is 0.75. So 0.15 times 0.25 is 0.0375. And then 0.15 times 0.75 is 0.1125. And this plus this in my check should equal that. It does. When I add across, I should end up getting 0.845. And adding across this way, I get 0.155. And if I add these two together, they should sum to one whole. If they've done that, then we have a pretty good opportunity that our work is good. So number one, what is the probability, or what proportion of little goblins in the land of Nod do not carry the slobbering gene? What proportion of the little goblins in the land of Nod do not carry the slobbering gene? Little goblins, no gene, 0.155. Number two, what is the likelihood that a randomly selected adult female goblin does not carry the slobbering gene and her little goblin offspring carries the slobbering gene? Now I see and I go, gosh, this is an intersection problem. All right, so what's the likelihood that a randomly selected adult female goblin does not carry the slobbering gene? So the female not gene, so this is this column. And her little goblin offspring carries the gene. So little goblin with the gene. And when I look at that, I see that I have an intersection. My cross is at 0.0375, so number two is 0.0375. Looking at number three, what proportion of little goblins have the slobbering gene or have a biological mother who has the slobbering gene? As soon as I see the word or, I think union. And as soon as I think union, I think, gosh, I need to use the general addition rule. And remember, the general addition rule is this: the probability of A union B equals the probability of A plus the probability of B minus the probability of A intersect B. All right? So, what proportion of little goblins have the slobbering gene? So, the little goblins with the gene, that's 0.845, that's its value. Or have a biological mother who has the gene. Well, biological mother with the gene is 0.85. And by the way, if I just added those two numbers up, it's greater than 1, so I have a problem. So, all right. Well, here's the problem I have. We have to subtract out the intersection. So the intersection is 0.8075. So when I plug this in a calculator, 0.845 plus 0.85 minus 0.8075, I end up getting 0.8875. All right, and that would be my answer. Once again, it was this plus this minus the intersection. And I knew that because of the or telling me that it was a union. Given that a randomly selected little goblin has a slobbering gene, what's the likelihood the female also has a slobbering gene? All right, as soon as you tell me the word given, I hear the word given and I go, gosh, given's in the denominator. I'm going to have an intersection on top. In this case, given the little goblin has the gene, that's 0.845, what's the likelihood that the female or the mother, so the mother has the gene, so that's 0.8075 because this is my intersection. All right, so here's my intersection. And when I divide that out, 0.8075 divided by 0.845 equals 0.9556. Excuse me, it's a little bit off the screen. 0.9556. If I can find a pen that I like, I'll use this. Once again, little goblin has the gene. This is my given right here. Female has the gene. This makes my intersection right there. All right. So here is my given, which was my denominator. Here's my intersection, which was my numerator. All right, so that's number 4. All right, moving on. Sitting here without sticky notes. So given the probabilities M equals 0.6 and MUD is 0.65, what probability of D if M and D are mutually exclusive? All right, so here we go. As soon as I see this union sign, I think general addition rule. So in this case, probability of M union D equals the probability of M plus the probability of D minus the probability of M and D. All right, so probability, let's start plugging in what we know. We know this is 0.65. We know that the probability of M is 0.6. We don't know what D is, and we don't know what the intersection is. But they gave us a hint, a big one actually. They said mutually exclusive. Mutually exclusive means we have no overlap, which means we have no intersection. So my intersection in this case is 0 because there's no intersection here. And so then when I subtract that out, I find out that D just equals 0.05 because that's supposed to be D. D equals 0.05. 0.65 minus 0.6 gives me 0.05. All right, so that's number 5. Moving on to number 6. Given the probabilities M equals 0.3, M union D is 0.7, what's the probability of D if M and D are independent? Well, once again, as soon as I see this union sign, I think the general addition rule. So the probability of M union D equals the probability of M plus the probability of D minus the probability of M intersect D. All right, so this is my union is 0.7, M is 0.3, D I don't know, minus the intersection. Well, I have a little bit of a problem. I don't know what that intersection is, but they tell me they're independent. And what I do know is the probability of M, excuse me, probability of M and D, or the probability of the intersection. I should slide this up so you can see it. The probability of M and D equals the probability of M times the probability of D. Well, in this case, we know what M is. We know that M is 0.3. I don't know what D is. But I can now substitute this for that. And that's what I'm going to do. I'm going to substitute this in right up here. So this is going to be 0.3D. I know there's a coefficient of a 1 in front of this. So 0.7 minus the 0.3 is 0.4. So 0.4 equals, because I subtracted 0.3 from both sides, 1 minus 0.3 is 0.7D. Divide both sides by 0.7. And 0.4 divided by 0.7 equals 0.5714. All right, so the answer is 0.5714. D equals that. And that is for problem number 6. Okay? All right, and please remember, because they were independent, I could multiply. If they hadn't been independent, I couldn't multiply and we would have been stuck. All right, so that's number 6. All right, so the number of points of X is scored in a game has the probability of distribution below. So in other words, if I play the game, the chance of getting 0 points is 50%, 1 point is 30%, 2 point is 20%. And 0.5 plus 0.3 plus 0.2 adds up to 1 whole. So that makes sense for the distribution. That sums up. So the number of points obtained in one game is independent of the number of points in the second game. So they're independent, which means that we can multiply if we need to. When the game is played twice, there it is. As soon as they play twice, we should be looking at a table or a sample space. The sum of the number of points for the games could be 0, 1, 2, 3, or 4. If Y represents the sampling distribution of sum of the scores when the game is played twice, what's the probability that the sum is 2? So real quickly, let's go ahead and make our sample space because we know we need to since the game is being played twice. So we can get a 0 on the first game and a 0 on the second game. A 0 and a 1, a 0 and a 2. A 1 and a 0, a 1 and a 1, a 1 and a 2, a 2 and a 0, a 2 and a 1, a 2 and a 2. All right, so we're looking for where the sum is 2. Well, 0 plus 2, well, that does it. So 0, comma, 2. 1 and a 1, that does it. So this, or I could get a 2, comma, 0. All of those, 0 plus 2 is 2, 1 plus 1 is 2, 2 plus 0 is 2. That takes care of my sum is 2 right there. So the probability of a 0 is 0.5. The probability of a 2 is 0.2. The probability of a 1 is 0.3, but I need a second 1. The probability of a 2 is 0.2. A 0 is 0.5. So in this case, I end up with 0.1 plus 0.09 plus 0.1. When I add those together, I end up getting 0.29. Okay, so that was number 7. And once again, we're playing a game twice. You know you need to make a sample space. If you're doing something twice, it's either going to be you either need to make a sample space or you need to make a table if you're doing something twice. So you got to have some ways to see what your outcomes and combinations are. Number 8. An administrator at Reagan claims that 17% of the cars parked in the student lots at Reagan belong to teachers. What is the likelihood that in a random sample of 10 cars parked in the student parking lots, at least one belongs to a teacher? So basically, we have 10 cars. We could have 0, 1, 2, 3, 4, dot, 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 all the way to 10. So this is what we're interested in. We're interested in the probability of 1, probability of 2, probability of 3, probability of 4. And I have to do all those individual probabilities, or I can make it easy on myself and do the 1 minus the probability that none of the cars belong to teachers. Well, what's the probability of a car belonging to a teacher? The probability is 0.17. The complement means it didn't belong to a teacher. So this is my complement. 83% of the cars don't belong to the teachers. So I want the probability that it doesn't belong to the teacher, but I need to have that happen 10 times. So that's my work. So here we go. 1 minus 0.83 raised to the 10th power. And I end up getting 0.8448. Now that's using what we knew prior to the test. Now I could have looked at this as a binomial, or I now can look at this as a binomial because you know how to do binomials now. Prior to this week, you wouldn't have been able to do this, so you couldn't have done this for this test. For the test, you wouldn't need to approach it this way. So if I were showing my work for the binomial, I would go, you know what? This is 10 choose 1 times, and then it's 0.17 was our probability to the first power. Then 0.83, 10 minus 1 is 9, plus dot, 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 plus 10 choose 10, 0.17 to the 10th, 0.83, 10 minus 10 is 0. Okay, but how does that relate to this? Well, first off, let's go with what we do in a calculator, just so I can do this as a reminder. So 1 minus, because it's an at least problem, we know it's a binom CDF. We know our trials are 10. We know our probability is 0.17. And we always subtract out the value, the highest value we don't want, which in this case is 0. So let's do that in a calculator to verify we get the same result. So 1 minus second vars binomial CDF, trials are 10, probability is 0.17, x is 0, and there it is, 0.8448. Now, how did we make the jump from here to this? How does this relate? Well, really, we're doing 1 minus the probability of 0. So we're doing 1 minus, well, what's the probability of 0 if we're using a binomial? Well, we'd go 10, choose 0, 0.17 to the 0, and then 0.83 to the 10th. This part right here is just 1. And look, we have 1 minus 0.83 to the 10th power. So 0.8448. Okay, so that's using the binomial. So now that you know how to use the binomial, if you prefer the binomial for that type of problem, feel free to use it. Okay, so number 9. A weighted 6-sided number cube is numbered with one of the numbers 1 through 6 with a different number appearing on each face. On this number cube, the probability of a, excuse me, let me slide this, you can see it. The probability of a 1 is 0.2, the probability of a 2 is 0.15, the probability of 3 is 0.6, the probability of a 4 is 0.15, and the probability of 5 is 0.2. 2 number cubes will be tossed. Of course they will. Such that will be tossed and the sum of the numbers appearing on the faces that land will be recorded. What's the probability of rolling doubles? Well, first off, what is rolling doubles? Rolling doubles is rolling a 1-1, a 2-2, a 3-3, a 4-4, a 5-5, or a 6-6. All right, so that's the probability. So what's the probability of rolling a 1 and a 1? Well, that's 0.2. but I have to do it twice. Probability of a 2 and a 2 is going to be 0.15 times 0.15. The probability of a 3 and a 3 is going to be 0.1 times 0.1. Probability of a 4 and a 4 is 0.15 times 0.15. The probability of a 5 is 0.2 times 0.2. But I have a problem. I don't know what 6 is. So let's do this. 0.2 plus 0.15 plus 0.1 plus 0.15 plus 0.2 plus x, that's the probability of 6, has to add up to 1. All right, so let's go through the work and figure out what that is. 0.2 plus 0.15 plus 0.1 plus 0.15 plus 0.2. So that equals 0.8. So 0.8 plus x equals 1, so x equals 0.2. So the 6 is a 0.2. So this is 0.2 times 0.2. So here we go. We need to add all that up. 0.2 squared plus 0.15 squared plus 0.1 squared plus 0.15 squared plus 0.2 squared plus 0.2 squared. And I ended up getting 0.175. So the answer to number 9 equals 0.175. All right. I did this because I knew it had to be a valid probability distribution. It had to sum to 1. So my probability of the 6 is 0.2. And I needed 2 of each one. So I just squared the probabilities and summed them together. Number 10, 30% of candies in a bag are brown, 10% are red, 20% are yellow, 15% are green, and the rest are blue. The 5 candies are drawn with replacement. What's the probability that the 5th candy drawn is the first one that's blue? Well, first off, they say with replacement, so the probabilities aren't changing. And we happen to have brown is 30%, red is 10%, yellow is 20%, green is 15%. They didn't tell us what blue is, so we're going to have to figure out blue. We know that it has to equal 1 whole to be a valid probability distribution. So 0.3 plus 0.1 plus 0.2 plus 0.15 equals 0.75. So the probability of blue, so this is 0.75 plus blue equals 1 whole. All right, so 1 minus 0.75 tells me that the probability of blue equals 0.25. It says, and what is the probability that the 5th candy drawn is the first one that is blue? That means 1, 2, 3, 4, 5. This is blue. And these are not blue. So this is 0.75. And of course, you could have written, instead of showing all that, you could have also just written 0.75 to the 4th times 0.25. I just find that the blanks, if I use the blank method, I'm less likely to make a mistake. Or if I start off with the blank method. 0.75 raised to the 4th times the 0.25, and I end up getting 0.0791. Okay, so that's the answer to number 10. Number 10 is 0.0791. Number 11. A machine has 5 components, and if any one component fails, the machine fails. 3 of the components have a 98% chance of not failing. 1 of the components has a 97% chance of not failing. And the last component has a 99% chance of not failing. It is reasonable to assume that the components are independent. That's important. That means we can multiply. What's the likelihood that the machine fails? So first off, everything we're given was not fails. And it also says if any one component fails. So we have 5 components. We could have 0 fail, 1 fail, 2 fail, 3, 4, or 5. If this fails, it fails, this fails, it fails, this fails. So I could figure out the probability of each one of those. It's a whole lot of work. Or I could find the probability that it doesn't fail. So in this case, 1 minus the probability of 0, which would be the probability that the machine doesn't fail. Well, the probability that none of them fail means 1 minus the probability that they all work. That's a K. All right, all work. So what is the probability that they all work? Well, we have 5 components, so let's do them. All right, and it's an independent issue. So we have 5 blanks, 1, 2, 3, 4, 5. So the probability the first one works is 0.98. Matter of fact, the first 3 are 0.98. One of the other components has a 0.97. And the last one is 0.99. Once again, they fail independently, so I can subtract them. I can multiply them. So 1 minus 0.98 times 0.98 times 0.98 times 0.97 times 0.99. Oops. So real quickly. So 1 minus 0.98 times 98 times 98 times 97 times 99. And I end up getting 0.962. 0.0961, or if you wrote 0.0962, of course you receive full credit for that. And that's question number 11. Moving on to number 12. Each person in a random sample of adults indicated his or her favorite ice cream flavor. There's a table. What proportion of people sampled were in the 30 to 50 category or preferred chocolate? So basically, we are looking at the 30 to 50 or preferred chocolate. All right. As soon as I see or, I go, okay, this is a union problem. So I should probably go ahead and write down my general addition rule. Probability of A union B equals the probability of A plus the probability of B minus the probability of A and B. All right, so probability of 30 to 50 is going to be 1 over 108 over 314 plus 99 over 314 minus my intersection of 22 over 314. So 108 plus 99 minus 22 equals 185 over 314. And I get 0.5891. Oops. 0.5891 or 0.5892. It's up to you. All right. Either one receive full credit. All right. So for flights from a particular airport in January, there's a 40% chance of a flight being delayed because of icy weather. If a flight is delayed because of icy weather, there's a 20% chance that the flight will also be delayed because of a mechanical problem. If a flight is not delayed because of icy weather, there's a 10% chance that it will be delayed because of mechanical problems. The table organizes the above information. Given that the flight was not delayed because of ice, what's the likelihood that it did not have a mechanical problem? So As always, I see the word given. I go, okay, I'm going to write that down because I know it's a given problem. And since it's a given, I know that there's going to be an intersection on top of it. All right? So given the flight was not delayed because of ice. Oh, that means I'm looking at the ice column. This is what they given me. And then I said, oh, was not delayed. That means this one. All right? So be real careful that you choose the right one. So this was not delayed because of this. So this is 0.6. What is the likelihood that it did have mechanical delay? My intersection. So in this case, once again, not an ice delay, but we had a mechanical delay. So 0.06 over 0.60, 0.06 divided by 0.6, and we end up getting 0.1. So our answer to number 13 is 0.10. And this is what we needed to see for work right here is the 0.06 divided by the 0.6. Okay, number 14. Apparently this problem gave people a lot of trouble. A parent has two children to get ready for school. One who is in high school and the other is in elementary school. The time it takes one child to get ready is independent of the other. That's probably important because it means I can multiply if I need to. The probability that both children will be on time is 0.15, so both is 0.15. The probability that the oldest child will be on time and the youngest is not is 5%. What's the probability the youngest is on time from school? Well, I look at that problem and there's a lot of information and it doesn't make a lot of sense to me. But I do notice that I have two things. I have a younger child and an older child. Maybe a table will help. Maybe it won't. But I always find that, you know what, if I got a couple things to work with or I can't make sense of things, the table's a nice organizational tool. And when you don't know where to start, you can always go, hey, I know one goes there. What do we do know? We go, okay, we have an older child that's on time. Older child on time, which means we also have an older child that's late. We happen to have a younger child that's on time, and sometimes we have a younger child that's late. Are there any numbers I can fit in anywhere? When I look for a single variable, I don't see it, but the probability that both children will be on time is 0.15. There was no condition on that. They didn't say if this happens or of that. They just said, hey, both children are on time 15% of the time. And if I ask you just to read that thing, oh yeah, both, so that goes there. The probability that the oldest child will be on time, and again, this is another intersection, child is not on time is 5%. So this is 0.05 because the older child's on time, youngest child is not on time, or youngest child is late, 5%. So guess what? That means the older child is on time 20% of the time. This is 0.80, and I'm just filling that in just because I now can. I don't know if I'll need it or not. What did they ask me for? What is the probability the youngest child is on time? This is what I'm looking for. I don't really have any other information except for the fact that I know that it's independent. And because it's independent, I go, wait a second, I do know that something about that. The probability of A and B equals the probability of A times the probability of B. Okay, so what do I have? I have the intersection because I have this 0.15 equals, I have A, the older child's on time 20% of the time, but I don't have B. Divide both sides by 0.2, and let's see what happens. 0.15 divided by 0.2 is 0.75. So this number is 7.75. Now I want you to consider this real quickly. We are saying that this number times this number equals an intersection. And they told us they were independent up here, which is why we can do that. So the answer to number 14 is 0.75. Number 15, approximately 4.5% of all children born in a certain region are from multiple births, that's twins, triplets, etc. Of the children born in the region who are from multiple births, 20% are of children born in the region who are from single births, 10% are left-handed. Wow, that's a lot. Nice that they wrote the table out. What's the probability that a randomly selected child from this region is from a single birth and is not right-handed? All right, so be real careful. Probability that randomly selected child from this region is from a single birth. Okay, that means they're this, because that's a single birth, and is not right-handed. Well, if they're not right-handed, that means they must be left-handed. They didn't condition it on anything. There wasn't any given. So my answer is purely just the intersection. And this right here tells me I'm looking for an intersection. So the answer to number 15 is 0.0955. Okay, please make sure this is all written neatly. And before you upload everything, make sure it's written neatly, orderly, so that we can see your work and give you the points that you have earned. Thank you.